Hi, my name is Dennis Rush, and my partner is Andy Nillipore, and we're here to tell you about confidence intervals and tests for the slope of a least squares regression line. So before we get into this, you guys need to know the conditions for inference. You can remember this using the acronym LINER, which stands for linear, independent, normal, equal standard deviation, and random. So to check for this, for linear, you have to make sure there's no leftover pattern and there's a residual plot. For independent, you check the 10% condition. For normal, it's a little bit trickier because you actually have to make a histogram or normal probability plot of the residuals and ensure there's no clear skew or outliers. For equal standard deviation, you have to check that the vertical spread of the residuals around the line residual equals 0 should be roughly the same across all x values. And for random, the data should come from a well-designed random sample or experiment. So when we're doing a test for the state and plan, generally our null hypothesis is beta equals 0, which means there's no linear relationship between the explanatory and response variables. If we're testing whether or not there's a linear correlation between x and y, our HA is going to be beta is not equal to 0, so it's two-tailed. For positive, it's this, and for negative, it's that. In this case, beta is the slope of the true population least squares regression line stated in context. So when you define it, make sure you put context. For the plan, we just say this, we're doing a t-test for slopes or for beta, and we have to check the linear conditions on the slide before. For the do and conclude for tests, you have to find the test statistic by hand using this formula, where B is the sample least squares regression line slope, beta is the null hypothesis slope, SEB is the standard error of the slope. Usually you're given this, but if you ever have to calculate it by hand, you have to use this equation. And you have to know the degrees of freedom, which is n minus 2 instead of n minus 1 like usual. Then you find the p-value using the t-distribution table or tCDF. Make sure to multiply by 2 if the test is two-tailed. And then you conclude like you normally conclude using this statement. If the p-value is less than alpha, we reject the null hypothesis and conclude that there is convincing evidence of a linear relationship between the explanatory and response variables. So for intervals, it's a bit different. For the state, we want to estimate the slope beta of the true population regression line. Plan, it's the same. We just have to check the linear conditions. For do, we have to find a C percent confidence interval using this equation, B plus or minus T critical value times standard error of B. Here you calculate the T critical value with degrees of freedom n minus 2, either using a T distribution table or using the inverse T command. And then you just plug everything you know in, and you find the lower bound and upper bound. To conclude, you say we are the C percent confident that the interval from the lower bound to the upper bound captures the slope of the true population regression line relating the response variable in context to the explanatory variable in context. So sometimes you're going to have to read computer output like in this mini tab as you can see. And we're not often given the P and T values in this computer output, so you may be asked to find these, which is what we just explained in these. But as long as you know the coefficient and the standard error coefficient of the explanatory variable, you're fine. If the p-value is given, then no calculations are necessary. Like in this case, the p-value is given at 0.000. Since raw data is rarely given, the only statistical functions you will usually need are tCDF to find the p-value and inverse t to find the t critical value for a confidence interval. But if somehow you're given raw data, you have to use the linreg t-test and the linreg t-in commands on your calculator. Um, Hopefully we'll never have to use this because we've never seen it. But if you do, you have to write the x coordinates in one list and y coordinates in another, and then input the confidence level for an interval or the alternate hypothesis if you're doing a test. So then there's their interpretations. We've already seen both of these, the standard deviation of residuals and standard error of the slope. You guys can pause the video and read them if you want to. Um, Sometimes you actually have to determine which of several transformations does a better job of producing a linear relationship. Usually you're comparing power model and exponential models. In power models, you plot y versus x to the p. If you want to make it linear, you're plotting log y against log x. And for exponential model, you just plot log y against just x. After transformations, you have to check which residual plot has the most random scatter, and that is the one that produces the best linear relationship. Some common mistakes are not multiplying the p-value by 2 for two-tailed alternate hypotheses, not checking every condition in linear, um, calculating the degrees of freedom wrong. Remember, it's n minus 2 and not n minus 1. And sometimes after transforming data, you just mess up. You forget to use transformed x variables or undoing the transformation of the y variable when using regression line to make predictions. So here are some released FRQs. They're good practice. Thank you very much.